Hello, everyone, and welcome to today's webinar, Dynamic Satellite Simulation for Thermal and EOIR Sensor Radiance Predictions. My name is Chris Niva, Marketing Operations Coordinator at Thermal Analytics and host of today's webinar. Our presenter today is Dr. Corey Packard. Dr. Packard is a Principal Engineer and Director of Research, Engineering, and Product Management here at Thermal Analytics. He has more than 20 years of experience in remote sensing and physics-based simulation, with his primary technical focus being EOIR signature prediction. Other technical efforts of Dr. Packard involve field test validations, phenomenological investigations, software development support, and predicting the behavior of optical sensor systems in turbulent atmospheres. Throughout this presentation, you may submit questions in the questions box and we'll review them at the end. We are also recording today's webinar and we'll be sending you the link following this presentation. And with that, Corey, if you're ready, you may begin.
Thanks, Chris. Good morning, everyone. Thanks for dialing in for this webinar on dynamic satellite simulation. I'd like to start this morning with a quick agenda slide to show some of the things we're going to cover in today's webinar. I'll start by talking a bit about the motivation for this work and a quick review of the orbital physics that we're going to take into account with our simulation methodology. And after going over a concise description of the approach that we're taking, I'll show some excerpts from a thermal validation that we published earlier this year. Upon showing that thermal validation, I'll explain how solar panels and battery cells can be incorporated into these sorts of thermal electrical simulations. And upon doing that, I'll share some interesting results from both low Earth orbit and GEO scenarios. And that's going to include some thermal predictions as well as some infrared signature results. And that as well as some excerpts from a presentation that we published this fall. I'll end with a few conclusions to kind of wrap things up and have a bit of time for Q&A at the end. So that's the agenda for today. And I'll start by talking a bit about the motivation for this work. So as most of you are probably aware, small satellites can suffer from thermal problems, and that comes from having miniaturized high power components and reduced radiative surface areas where that heat can be dumped to space. Can be complicated to get the energy balance right. And so satellite designers like to use simulation to make sure that the key components in the satellite are going to stay within acceptable temperature limits during the extremes of the orbit. Then going beyond temperature prediction, there's some defense applications as well where the signature of orbiting payloads might be of interest. And so these are some of the different motivations for this type of simulation work. And so what we're going to look at today, I'm going to show a validation of our commercial heat transfer software, MuSES, for a dynamic satellite that's orbiting the Earth. After that, I'm going to show how this methodology can be extended to include thermal electrical coupled simulations where we're including solar panels and batteries into our MuSES simulation. And then we're going to apply that more advanced methodology to doing dynamic infrared signature prediction of payloads that are in GEO and LEO orbit. So here's a quick look at some of the orbital physics that we want to take into account. We've got this cartoon depicting orbiting satellites. And so some of the things that we want to look at here is the radiation exchange between the satellite and Earth. We want to look at the radiation exchange between the satellite and space. Then we've got direct solar loading coming from the sun and reflected solar bouncing off the Earth and lighting up the satellite as well. And then, of course, we've got internal radiation and conduction inside the satellite. So these are some of the different thermal physics that we want to include in our methodology. So here's a quick summary of the low Earth orbit and GEO differences from a energy balance perspective. So if we first start looking at low Earth orbit, that cartoon there is kind of depicting the scenario that we've got. The view factors from the satellite to the Earth are going to be pretty significant in this case due to the proximity of the payload to Earth. And so solar loading is going to dominate this scenario, both direct solar loading and Earth reflected solar loading. But because of the proximity to Earth, the thermal radiation shouldn't really be ignored. That should be incorporated. And then contrasting this with the GEO scenario, where the satellite's much farther away from Earth, the view factors from the satellite to the Earth are quite a bit smaller. So the Earth emitted thermal radiation is not as dominant. It's a smaller factor, and the Earth reflected solar is not quite as important. Direct solar is really going to dominate, but our methodology includes all those things. So we're not discounting them just because they're smaller, but just showing what's going to dominate different types of scenarios. Another interesting difference between these two is what percent of the orbit is in shadow. So for a typical low Earth orbit path, that eclipse is going to be around a third of the path, whereas for a GEO payload, it might be closer to 5%. So it gives you an idea of the relative size of the eclipse. So moving on to the simulation methodology that we're going to use for satellites here, I want to first start by explaining a bit about MuSES, in case some of the people dialing in aren't as familiar with MuSES and what some of its different applications are. So I'm going to use this ground vehicle to the right as a way of explaining MuSES, but there's lots of different types of targets and scenes and objects that can be simulated here. But at its core, MuSES is both a transient thermal solver and an EOIR rendering tool. And so the inputs to the tool is going to be 3D geometry in the form of a surface mesh, description of the materials along with the thermal properties of those materials and what parts of the geometry that's applied to, heat sources for various components, which might include engines, exhaust systems, electronics, and so forth. Then we apply boundary conditions, and that's going to be things like weather for terrestrial applications, and atmospherics if it applies. So that's kind of the inputs. On the output side, the first step is going to be to predict physical temperatures, where we're predicting the temperature of each element in the 3D model. And that's going to be then followed by predicting what that object or scene is going to look like to an EOIR sensor. And that sensor can be anywhere from the visible band all the way up to the long wave infrared band. And so we can see we can predict what a sensor platform would see with a certain field of view and range and so forth. And then moving beyond just that, we also can have more complicated scenes where beyond just the object itself, there can be a complex scene, and we can look at the contrast of the object against its scene and so forth. So, this is just a high-level description of what MuSES is, so you kind of have that in mind as we go forward and apply this to satellite simulation. So this slide is a quick summary of our methodology. So we start by creating a detailed 3D model in MuSES, and then using the transient physics-based heat transfer solver that's in MuSES to calculate the physical temperature of that payload over time as it's orbiting and its boundary conditions are changing. And MuSES is going to help us incorporate the primary environmental forcing functions that I showed on that physics review, which includes direct and reflected solar radiation, the thermal radiation that's coming from the Earth, and the thermal radiation that's escaping to space. And a cotherm process can be used to automate this kind of dynamic simulation with just a few simple user inputs. And some of the interesting things about that cotherm process involve multiple orbit propagation options, the ability to automate that transient thermal simulation, as well as post-process the results and visualize them. So these graphics kind of depict the situation when it comes to thermal radiation. So we've got the thermal radiation exchange with the Earth and the payload, as well as going to space. And this is accomplished via view factors that are automatically calculated by MuSES. So we're calculating the view factors to Earth and to space. And so both the attitude and the altitude of the satellite are going to influence these view factors. And that's going to let us automatically calculate the thermal radiation exchange between the payload and the Earth and space. And that's on the thermal side. On the solar side, again, we're going to use these view factors to calculate the direct solar loading on the satellite, as well as the solar loading on the Earth, how much reflects, where that reflects to, and how much of that reflected solar is eventually absorbed by different elements of the satellite. So that's a brief description of the approach that we're taking. And now I want to switch over to showing a few excerpts from the ICES paper that we presented this summer that was focused on the thermal validation of a small satellite simulation model. And so for this published paper that we did, we focused on a 3U CubeSat, and essentially what we set out to do was to run a simulation using the boundary conditions from another published paper that was back in 2018 on this 3U CubeSat and show how we could match those published temperatures. So the CubeSat is depicted at the lower left there, and we can see that, obviously the cube has 6 sides to it. 3 of the long sides of the 3U CubeSat have solar panels on them, and that's the yellow indicated there. The orbit that we simulated is shown at right with the orange line showing the path around the Earth, and the translucent gray is showing the eclipse region where the sun is kind of directly overhead of that path. So that's the circular LEO path that we're going to be simulated and showing this morning. So taking a look at that energy balance at different points of the satellite's path around the Earth, we see that when the sun is directly overhead, kind of in line with the satellite and the Earth as depicted with that real small graphic there, we can see that direct solar is going to dominate the energy balance, followed by the Earth reflected solar, and then the thermal radiation making up only about 5% of that energy balance. A little bit later, when the payload has orbited and is kind of 90 degrees away from that collinear geometric relationship, we see that the thermal radiation from Earth starts to play a little bit bigger factor. And then once we get 180 degrees away and the payload is now sitting directly in that eclipse region, the thermal radiation is going to dominate due to the fact that it's in the shadow region. So when the satellite's exposed to the sun, the temperature is going to be primarily determined by solar radiation, though not exclusively. And then when it's in eclipse, that radiation exchange with the Earth and space is going to dominate. So now we're going to take a look at how well we compare to the published results with all of these different environmental forcing functions. So first we take a look at the thermal radiation exchange that's coming from the Earth. And in these graphs, the black lines or bars correspond to the published paper that we were comparing ourselves against, and the green is the MuSES prediction. So we could see that the thermal radiation that's coming from the Earth and is being absorbed by the satellite matches the publication really well on all 6 faces of the cube. And moving on to direct solar radiation, again, we see a really good correlation between the MuSES predicted values and the published values. And finally, looking at the Earth reflected indirect solar radiation, we see again MuSES matching both the shape of the curve and the magnitude of the curve. And so we would expect that if we match these boundary conditions really well, then our temperature prediction would match quite well. And that's what we see here. So the cartoon that I'm showing in the upper right has a single node inside the satellite, and that's what was assumed by that publication, that we've got a single node satellite. And so the faces of the cube are being used to gather the boundary conditions for the energy balance that's being computed on the single node, which is kind of like a 1 kilogram lump capacitance on the inside of this CubeSat. And so the graph in the lower right there, the black is the published result and the green is the temperature prediction by MuSES. And so MuSES matches really well, to within 0.2 degrees Celsius of the published work. And so we see a few different animations showing solar flux and thermal animation on the outside of the payload. But predicting just the temperature of a single node satellite is not really our interest here. It's a good starting point, but now that we know we can match the external environmental boundary conditions, we want to show how a more realistic satellite can be handled by incorporating solar panels and battery cells into the simulation. And so what we want to do is move beyond this single node approach to something a bit more realistic. And so this diagram depicts solar panels, a battery pack with 8 different battery cells inside it, and different internal circuit boards with chips on them that are going to be heating due to the mission of the satellite. So this is a more interesting scenario that we're going to start taking a look at for the rest of today's webinar. So we can predict the temperature of these different internal components over time. The graph there kind of shows temperature oscillation during multiple successive orbits around the Earth, and the animation at the lower right is showing temperature oscillation of those different components over time. So these are the sorts of things that can be computed and visualized. And then one interesting application of the ability to predict these temperatures is to be able to look at when the components are inside the temperature envelope that they need to stay in, and when they exceed that and thus kind of move outside of the desired operating range into a more marginal state. So we can use design temperature thresholds inside MuSES to look at which components are going to pass, be marginal, or potentially fail and be outside of the limits, and therefore some type of passive or active thermal management might be a good idea. Here's an example of a few more of these visualizations that we can see. The animation shown at right, we made the outside of the satellite and solar panels translucent, so we can see some of the internal components there just for context. So now we'll talk a little bit about how we incorporate the battery pack and solar panels into our simulation. So first, with the battery, for the rest of this webinar, we're going to be looking at an 8-cell battery pack that's configured in a 4S 2P topology. And the approach we're taking is to do a coupled thermal electrical solution where MuSES is handling both the electrical and the thermal part of the simulation. So we're modeling the electrical behavior of the battery with an equivalent circuit. And when we're computing the battery temperature in the transient temperature solution, we're considering the impact of the current that's being drawn by the electronics, as well as the current that's being supplied to the battery by the solar panels. And we're monitoring the state of the charge of the battery over time to make sure that it can support the power budget of the satellite throughout the mission. So that's kind of a high-level, simple description of how we're handling the battery, and we've got more presentations that go a lot more in depth into this. Similarly, the solar panels, we've got 9 different solar panels that are triple junction solar cells, 3 each on 3 different long sides of the 3U CubeSat. And we're assuming a nominal efficiency of 29%, but with a temperature coefficient where the efficiency of these solar panels is going to change with the temperature of the solar cell. And so by computing the temperature of the solar cell, that affects the efficiency, and the efficiency thus also affects the temperature, hence the need for a coupled approach. So we've got a few different ways that we can model solar panels, including equivalent circuits. So beyond looking at just the efficiency impact due to the temperature dependence, we also incorporated the fact that the incidence angle of the solar radiation impacts efficiency. And furthermore, radiation degradation due to exposure in space can also be considered. We neglected that in this simulation, but we'll be presenting that in the future. But that can easily be considered in these sorts of simulations. So now that I've shown at a high level how we can incorporate both active solar panels and active battery cells, I want to show some interesting thermal and infrared results by applying this methodology to a LEO and a GEO scenario. And these are some excerpts of our AMOS paper that we presented in Maui in September this year. So there's a few different orbital remote sensing scenarios that someone might be interested in. Here's a few. You might have a space-to-space scenario where you're interested in looking at the signature of a satellite from the perspective of another orbiting payload. Another scenario is called overhead persistent EOIR, and that's where you've got an orbiting sensor platform that wants to observe something going on Earth, and so it's looking through the atmosphere. And finally, Earth-based observations, where you've got maybe a telescope on Earth that's looking up through the atmosphere at orbiting payloads. So all of these might be of interest. Today, the results I'm going to show you are more in the vein of the space-to-space or Earth-based observations. And again, what I'm showing here is an excerpt from the paper where we show broader results. So we're going to look at two different scenarios here. The first is a low Earth orbit scenario that is inspired by a Starlink orbit. So we used some two-line element data from a SpaceX Starlink satellite and used that to create our orbit propagation. The figure at the far right there shows which portions of the path are illuminated by the sun versus when the payload's going to be in shadow. So that gives you an idea of what we're looking at. And the second scenario that we're going to look at is a GEO scenario where we use the GO-17 satellite to supply the two-line element data to create our path. But we're going to be simulating this 3U CubeSat in both of these cases, just using these orbits for the boundary conditions. And again, at the lower right there, we see just a portion of the GEO orbit and when it's going to be in shadow versus lit by the sun. Okay, so there's a lot going on here. I'll explain each of these in detail one at a time, but I just wanted to show them all at the beginning so you could kind of see the interdependency between these. So these are both thermal and electrical results from a MuSES simulation for that low Earth orbit scenario that I just talked about. And so the battery and the solar panels, all these things are linked together and interdependent because of our thermal electrical coupled co-simulation approach. And so I'm going to kind of talk about each of these. On each of these figures, I'm going to use these gray translucent bars to show where the eclipse region is, just so it's a little bit easier to picture what's driving the oscillations that you see. And we'll start by talking about the battery cell temperature. So what we're looking at here is multiple successive orbits of this LEO payload. And we see the battery cell temperature starting at a cooler temperature and then going up, and it's kind of oscillating as it's going from shadow to being lit by the sun. And we also see a temperature difference between two different cases. So, you know, the rest of the way out, you're going to see a lot of red line compared to black line comparisons. And in all of these figures, the black line corresponds to a satellite where the internal electronics are turned off. So we've got no load. Whereas the red lines correspond to a 3-watt internal load. And that's those circuit boards that are going to be drawn energy from either the battery or from the solar panels. So we see a temperature difference in the two satellites due to that internal heating of the electronics. So not only does the battery cell temperature oscillate in this particular demonstration model, but the solar panel temperatures change as well. You know, they cool off once the satellite is in shadow, and they warm up once it's in the sun. And again, there's a temperature difference due to the presence or absence of internal heating. Now, the solar panel temperature, as we discussed, impacts the efficiency of the solar panel. And so we could see a slight efficiency difference between the red and black curves due to the temperature of those solar panels. And we could see that the efficiency is not a flat line at 29%. The efficiency of the satellite affects the available power that's being harvested by the solar cells. And so we see during the eclipse regions, there's 0 watts available. And then while the satellite is lit by the sun, we can predict how many watts are going to be harvested by those solar panels. And keep in mind that in all these demonstration models, we're just using a constant 3-watt load. So during the eclipse regions, there's no available power from the solar cell, so the energy is going to have to come from the battery cells. Whereas when there isn't an eclipse present and we see greater than 3 watts of available harvested solar power, then the solar panels are going to be able to keep up And then in that case, the excess energy can be used to charge the battery. Here we see the battery pack current, and it is negative during the eclipse regions because it's supplying the power that's needed to run the electronics. And then when we see that battery pack current listed as positive, that's when it's being charged by the solar panels and the excess energy that is available. And so what we see here with the black line is that the battery pack becomes fully charged and then isn't needed due to the lack of internal electronics. And so it just kind of flatlines, whereas we see the oscillation for the active satellite. And finally, we look at the state of charge here. So again, the black line is showing starting at a 50% state of charge being charged by the solar panels, but then the lack of load means it just stays fully charged for the rest of the simulation. Whereas the active satellite, we see that state of charge kind of oscillating between 55% and 75% due to the eclipse kind of coming and going. And so this can help you see if your battery pack is sized appropriately for the power budget of your satellite, whether you've got enough solar panels, and you can link all these things together and see all these quantities interplaying here. So then moving on to the signature prediction results, we're going to be looking at long wave sensor radiance predictions, and these are done by MuSES as well. So just for context, at the bottom, I'm showing the battery cell temperature and the solar panel temperatures as well. As a reminder. But what we're going to see here is that the higher temperatures coming from the active satellite is going to translate to a higher long wave infrared radiance. And that's because there's a very strong T to the fourth relationship between physical temperature and radiance in the long wave band. So these colored images that you see here, these are false color renderings that's being done in the 8 to 12 micron band inside MuSES. So these are band integrated sensor images. Panel A there is in units of radiance, and panel B is in apparent temperature, which is what the temperature would have to be if these were black bodies. But of course they aren't black bodies, but that's a unit that some people like to see. So one of the differences that you see here is the higher radiance on the right from the 3-watt load compared to the lower radiance with the inactive satellite. And that's going to show up as kind of a shift in radiance over time during the orbit. And so we'll show that to the right here, where we're taking all the pixels on the satellite and we're averaging those to get an average long wave radiance. And so the line plots to the right, the red and the black plots, those are transient results where the average of all the pixels on the left essentially gives you one value on the right. And then you would do these renderings at many different times throughout the orbit, average the results, which is done for you by MuSES, the averaging, and that forms these transient signature results on the right. And then we see a vertical shift between the black and the red lines, indicating how that temperature, that higher temperature of the active satellite turns into a shift in the long wave. So we see a radiance difference due to the temperature. So hopefully that makes sense, and I'll show something a little bit similar for the GEO scenario. Maybe one thing I'll point out here before I switch scenarios is that I realize these are highly resolved renderings that we're showing where there's quite a few pixels on target, and it's possible that if you were viewing the satellite from another satellite, the distance might be very great and the field of view might, and the detector resolution might make it difficult to highly resolve this. That's one of the benefits of simulation, is that you can predict a sensor that you might not yet own, or one that's being constructed but hasn't been finished yet. But this lets us look at a lot of different effects. But of course, the resolution wouldn't have to be this high. So I won't go into detail about that now. It just makes it a little bit easier to understand what's going on to use a high resolution detector like this. Okay, moving on to the GEO scenario. Again, these 6 figures kind of show how the temperature and electronic aspects of the simulation interplay here. And again, we'll be using these gray bars to show where the eclipse region is. So again, starting with battery cell temperature, we see the temperature warming up, then cooling down once the eclipse happens, and then warming up again. There is, in this case, no thermal control or management systems like battery heaters or anything like that. That can be simulated with MuSES. We left that out to kind of create a baseline case here for what it would do without many of those systems in place. Panel C here shows the solar panel temperature, and we see that change throughout the orbit. Again, there's a shift between the black no load case and the red 3 load cases, and we see cooling during the eclipse region, which we would expect. Here we see the solar panel efficiency, and again, there's a slight difference in efficiency due to the increased or decreased temperatures of the solar panels. And that efficiency then affects the available solar power. So this gives you an idea of the energy that's harvested during this particular orbit. And again, if you kind of superimpose a horizontal line at 3 watts there, that shows you what parts of the orbit there's going to be excess solar power and what parts the battery is going to need to do its job. And that kind of internal power budget and the capacity of the battery, those two things interplaying is going to show you whether the battery pack is sized appropriately for the mission of the satellite. Then we see the battery pack current here. Again, it's negative during the shadow where the battery needs to supply the energy, and it's positive where there's solar loading present to run the electronics as well as charging the battery pack. And in both the LEO and GEO results that I've shown, we're simulating a simple battery management system where the charging of the battery is disabled once the state of charge exceeds 90% and it's essentially fully charged, as well as when the state of charge goes below 10%, then the battery stops being able to supply energy. So that's the kind of limits that we're superimposing for this demonstration. And then finally, the state of charge. Again, we're assuming a 50% state of charge initial condition, and then showing how that charges or discharges throughout the simulation. So then transitioning from the thermal and electrical results over to the long wave infrared results for the GEO scenario. Again, we're going to see that higher temperatures lead to higher long wave radiances, as we'd expect. And in this false color graphic here, I'm showing 6 long wave 8 to 12 micron renderings and comparing them to each other. So what we see is 2 different columns of images, 3 rows each. Each column, the one on the left is the no load case, the 0 watt case, and the column on the right is the 3 watt active case. The first row is at 8 a.m. in the orbit. The second one is at 9:30, and the last one is at 11 a.m. And what we see, if you compare the images left to right, is that the radiances that you see on the image on the right are higher than the ones on the left, which is what we'd expect, higher temperature leading to higher long wave radiance. We also see that the colors change as you compare the different times to each other, meaning that if we look at these over time in a transient fashion, we're going to see some sort of oscillation. And in fact, that's what we see here. And again, if we take the different pixels, average those together to get a single value, a single radiance value for a particular aspect ratio and a particular time in the orbit, that translates to 1 point on the graphs on the right. And then if you do these renderings at many different times, you can form those black and red lines. So the 6 images that you see in the center there are represented by those 6 points on the line graph to the right. And I showed some kind of brown dashed lines showing the 3 different times in the simulation where the images correspond to. So hopefully that makes sense and kind of shows the kind of analysis that you can do in MuSES for these sorts of scenarios. And then I'm going to show an interesting comparison between shortwave and long wave analysis that can be done, and see something interesting and novel about this long wave result. So I'm going to compare some long wave results and short wave results. Before I do that, I want to kind of quickly explain um, the physics that are at play here so that these results make sense. So the image at the lower right there shows the electromagnetic spectrum. We see shorter wavelengths on the left, longer wavelengths on the right. The shorter wavelengths on the left, those are going to be bands like visible, near infrared, SWIR, whereas the longer wavelengths are going to be long wave infrared. Um, and so those shorter wavelength areas, visible, near IR, SWIR, those are going to be dominated by visible light being reflected. So light and light reflections is going to dominate in those regions. Whereas as you head towards the longer wavelengths, reflected sunlight is not going to be the dominant thing that we see in renderings. Rather, it's going to be emitted and reflected temperatures um, primarily. So we're going to see more of a light effect in the shorter wavelengths and more of a temperature effect in the longer wavelengths. It's a bit of a simplification, but that's the main thing that's going on here. And so what we see when we compare these two together is that there's a couple interesting things going on. Now I know there's a lot of lines here, but I'll explain. So again, this translucent gray region represents the eclipse. And we see a lot of lines here, but they fall into two different wavelength categories. So we have a whole bunch of different types of sensors being simulated. You see them marked there in the kind of bluish green box in the upper right. Those are all sensors that fall somewhere in the visible, near infrared, or SWIR band, shown at the bottom with the kind of teal outline. Whereas the two red lines that are on the upper graph, those are both long wave predictions. And again, that's the longer wavelengths. So we see two primary interesting things in this comparison. The first thing that we see is that during that gray eclipse region, there's still a long wave signature that's present. And that's because there is still a temperature of that satellite. So it's still emitting energy. And so that's visible to a long wave sensor. That long wave sensor can observe that temperature emission. And so you see the dashed and dotted red lines. The satellite is cooling during that period, but it's not absolute zero, and we can see that temperature. What you'll notice is that in that eclipse region, all the shortwave sensors, so all the visible, near IR, and SWIR sensors, they all flatline during that region. And that's because the satellite's not being lit up by the sun, it's not reflecting that energy, and so an optical sensor that's in those shorter wavelengths doesn't see anything. So what we see is there is some non-zero long wave signature in this region, and that's pretty interesting. Beyond that, we also see a discernible difference between the 0-watt and 3-watt payloads. And so that's interesting as well. And that's the effect that we showed earlier in the webinar. It's still present here. So by way of kind of wrapping up some of the things that we've seen today, we've shown that MuSES can be used to accurately predict the temperatures in a dynamic sense of orbiting payloads, so in a transient fashion. And as well, we showed how we can integrate solar panels and battery cells into these co-simulated coupled thermal electrical simulations, and that lets us predict the impact of harvested energy from the sun and the power budget based on the mission of the satellite and how the battery is going to charge and discharge, and we can kind of couple all those together. And that lets us accurately predict all the temperatures and the battery performance, and we can then use that to make sure that the key components of our system are going to stay inside the desired temperature envelope during the extremes of the orbit, and how effective the different passive and active thermal control systems might be that are being considered. Then beyond this, we showed how satellite signatures of LEO and GEO payloads can be predicted by MuSES, and there's a lot of different geometric scenarios that can be considered, including Earth-based observations, space-based observations, and overhead persistent observations of ground scenes. So with that, I'll wrap up and see what questions that you have. Appreciate your interest and your dialing in, and love to see what questions you have.
Yeah, thanks, Corey. Let's see. Is MuSES capable of even higher fidelity thermal simulations where additional passive and active thermal control systems are present?
Yeah, great question. So MuSES is definitely capable of that. We're kind of showing some foundational work here, starting with a real simple single node validation to show that the boundary conditions that are being predicted are accurate. And then we showed how to incorporate solar panels and battery cells. But definitely beyond this, other types of passive and active systems can be simulated for sure.
All right, thank you. Other than the thermal validation you showed today, has MuSES been validated previously for thermal and/or EOIR predictions applications?
Yeah, that's a great question. So yeah, today I showed a simple one node thermal validation of a satellite, but yeah, MuSES has been around for decades, and we've done numerous validations over the years, both thermal validations as well as EOIR validations in a variety of wavebands. And so some of the different field tests that have been done to validate it include ground vehicles, buried explosives, maritime vessels at sea, uh, human, human, personnel in scenes. Yeah, real wide range of different validations that we've done in all kinds of different cold and warm environments. So, yep, numerous validations. And if people are interested in specific applications, they can let us know, and we can follow up with them about those.
Thank you. How to apply the solar radiation to the spacecraft? Did you use the solar constant value with the new factor?
Mm. Yeah, so I'll keep it a bit high level here, and we can follow up more afterwards if needed. But there's a variety of ways that can be controlled. MuSES accepts a variety of different inputs to govern the solar loading of the simulation. That can be a constant value that's supplied, or something that varies over time. And then furthermore, the view factors that are automatically calculated are going to figure out the solar apparent area of the satellite and how much solar loading the different elements of the model are going to receive, both direct from the sun as well as reflected off the earth. Yep, so there's a variety of ways that can be applied and considered.
All right, thank you. Is MuSES capable of unresolved satellite simulations where fewer pixels on target for space-based payloads are available?
Yeah, that's a great question as well. So I know that the images that I showed, the long wave images that we showed with the false color palette, were pretty highly resolved, where there's a lot of pixels on target. And that would obviously imply either a pretty close viewing distance or a very narrow field of view. And that was kind of for demonstration purposes to make it a little easier to understand what MuSES is doing and how it's calculating things. But MuSES is certainly capable of simulating lower fidelity detector resolutions and larger fields of view, where you're going to transition from a highly resolved scenario to a more unresolved scenario. And so one way to think about that is that when MuSES is doing its renderings, it can cast, it uses a ray tracing method, and it can cast multiple rays for every sensor pixel. And then it can average those together to give you a physically accurate result that would come from a less resolved image. So one way to picture that is if you take the highly resolved images that I showed and you took all the pixels on the satellite and you averaged those, which I kind of explained we use to form those line graphs. MuSES can kind of do that for you, so that what you see is a lower resolution image where it's kind of calculating that higher resolution image and averaging those subpixels together to get the physically accurate pixel values. You can set it up to do that. And of course, if you wanted to then include other effects like atmospheric turbulence and other things, depending on your viewing scenario, there's a variety of ways that you can deal with that too. So yeah, good question.
All right, thanks. Well, looks like that'll do it for questions. So that will complete today's webinar. We appreciate you all for attending. Everyone will receive a follow-up email this afternoon containing links to download the presentation slides and watch the recorded webinar session. Thank you, Corey, and everyone have a nice day.
Thanks, everyone.